So today we'll be investigating the nature of space. And briefly, after introduction and a bit of motivation, we'll discuss a little bit of the physical nature of space as described in science, and then we'll get on to the nature of space and our personal experience. So, Okar Rinpoche, who's a Tibetan master, says that the fundamental dysfunction of our minds takes the form of a separation between I and other. We falsely grasp at an I on which attachment grafts itself at the same time as we conceive of an other that is the basis of aversion. So our suffering really comes from this distinction between I and other. And one of the ways that that distinction manifests is in space. So perhaps some of you will recognize this passage from another mystic. By naming myself I also unnecessarily name all that which is not I, the world, so that in every act of naming myself, I'm already implicated in the experience of duality or separation between I and that, self and world. Anyone recognize this so far?
Tom McFarlane.
Let me give you some more hints. But further, in order to name, I must compare. And by comparing, I must see the world as diverse and know these diversities as harbingers of joy and suffering, pleasure and pain, good and evil. And by distinguishing joy from suffering, pleasure from pain, good from evil, I'm impelled to seek the one and flee the other until everything reveals itself to be ultimately ephemeral and ungraspable. And I'm finally confronted with the image of my own ephemerality, which is the metaphor of death. Who recognizes that? Yeah, you? That's from the prologue of Naked Through the Gate by Joel. Which is really a paraphrase of what Okar Rinpoche was saying, really, that this distinction between I and other is the root cause of our suffering. And it also is the root of the experience of all these different objects in the world. And it starts with ourself, really. As infants, we learn to distinguish our own bodies and our own impulses and movements with objects we bump into, objects we want, objects we don't want, and so forth. So all of these distinctions, or at least many of them, take the form of distinctions in space. Really, we have our toy, and it's localized in space. We have our body, it's localized in space. And so these are boundaries within this thing we call space. And it allows for different things, and these different things have different locations. They might be near, they might be far, they might be close, and so on. And these all end up forming what's called props and the stage and the characters in the story of I. So every play has to have props and a stage and everything, and these are all objects that interact with each other within that story. And so in our experience, all of these objects that are created from these distinctions in space form really the material of this story. And in this particular story, as Joel's quote pointed out, it ends with the metaphor of our own death, which often prompts us to go on a spiritual path. So what is the nature of this space, though? It's the fundamental substratum upon which all these distinctions are drawn, and then we end up playing a role within this space. But what really is the nature of that space? So I'd like to investigate that with you a little bit this morning. We'll start by investigating physical space, and then we will come back and take a closer look at experiential space. So, physical space. Beyond the familiar objects, we have this idea that space is what contains physically not just the objects we're immediately in contact with, but the whole earth, And beyond the Earth, there's our solar system, all the other planets and the sun. And beyond our solar system is what's called our solar interstellar neighborhood, all the stars that are in close proximity to our sun. And beyond that, of course, is our whole galaxy, which is composed of billions and billions of stars, as Carl Sagan likes to say. But our galaxy is only one of a whole bunch of galaxies in what's called the local galactic group. And that's part of a whole supercluster of galaxies. And there's a whole local group of superclusters of galaxies, and those are contained within the whole observable universe. So this is just incomprehensibly vast, this physical space. And this is the current paradigm of science. Understands space as this container for all of this matter and energy that is just incredibly vast. And we're located in a small location on this tiny planet within the solar system and galaxy and so on. So, if you get more detailed about how science describes this space, it's more than just a container. It actually has a specific description of it because scientists want to be able to measure and find laws that describe the regularities between the measurements. So space has a particular structure within physics. And as this picture tries to illustrate, the current understanding of space is that it's a curved structure. This is what Einstein introduced in the last century with his general theory of relativity. Gravity is what is really the curvature of space. Mass tells space how to curve, and the curvature tells matter how to move. So if there's the Earth, for example, curves the space around it, and because the space is curved, a satellite orbiting the Earth follows a circular path instead of a straight one. So there's not actually a force of gravity between the two. So it's a smooth curved space that's related to gravity, as I said. But what really is the description of space per se? The physicists talk about how it's curved, but what is it that's curving? What is the description of space, really, that underlies this? We want to get to the heart of the matter here. Now, if you look at the global structure across a distance, this can be curved. But if you look at any one of these squares, locally, it's pretty flat. And so the smaller you look at an area, the more it's just like a flat space. And so in the physical description, any small piece of space is treated as if it were flat, but then you kind of put it all together and it ends up being curved in a global sense when it gets extended. So let's take a look at flat space and the mathematical description of the flat space, because the physicists used mathematics to describe this space and its properties. Now, one of the most fundamental features of space is its dimension. A point is a zero-dimensional space, and a line is a one-dimensional space because there's one way in which things can move through that space. A square is a two-dimensional space because things can move in two orthogonal perpendicular directions. And a cube is a three-dimensional space, and you can mathematically continue that indefinitely to infinite dimensional spaces if you want to. Now, the most fundamental, non-trivial of these spaces is the line. The higher dimensional spaces are really just extensions of the line in a sense. And so let's take a look at the line. How do we describe the space of a line? Well, we start by placing points on the line and then labeling them with numbers. We've all done this in grade school, of course. This is called the number line. And we associate numbers in order along this line, and that allows us to start to describe the structure of the space, because now we've labeled it and we can start to work with those labels. And in particular, we've labeled it with numbers, and numbers have particular properties. Some numbers are greater than others, and some numbers are less than others, and that corresponds to the property that some points on the line can be on one side of another point, other points can be on another side. And so the numbers are an arithmetic representation of that space, or at least of some properties of the space. So having drawn those points and numbered them, we can start to describe the space using numbers. And we need to do that in order to compare properties of space with properties that we're measuring, and measurements, of course, result in numbers. So once we have numbered these, we'll notice that we haven't numbered all of space. There are gaps between these points. So this starts to describe the space, but it's missing a lot because it's missing a whole bunch of points between every two numbers. So what do we do about that? Well, of course, we subdivide the space. So between points at 0 and 1, we divide that in half, and we get a point at half, and we divide that in half, and we get a point at a quarter, and an eighth, and all these other subdivisions. And this, of course, is exactly what a ruler looks like. It allows us to make more and more precise measurements by subdividing space more and more. And we associate with each of those points another number, which isn't a whole number, but which is a rational number, a ratio of two integers. And you can continue doing this indefinitely, really, because between any 2 points, there's always going to be another rational number that's halfway between them, the average of the 2 points. So, for example, if you have two arbitrary points A and B, you can take A plus B over 2, and that will be another rational number. A and B are rational, so you add them together, it's still rational. You divide it by 2, it's still rational. And you can continue that process indefinitely. So no matter how far you want to go, you can always divide space further. And so it might seem that this fills up all of space. And this property of being able to subdivide space further and further and further and further, really infinitely, can lead to some paradoxes. So here's a famous paradox of Zeno called Achilles and the tortoise. And Achilles runs twice as fast as the tortoise. In this illustration, that would be a pretty slow Achilles, but or a fast tortoise, however you want to look at it. Let's say it's a fast tortoise. So they're gonna go on a race, and Achilles is very generous, so he gives the tortoise a lead at the start of the race. He says, "Okay, you can start 16 meters ahead of me." So the tortoise starts at 16 meters ahead of Achilles, and then they run for a little while, and after a little while, Achilles, of course, will have run 16 meters. In the meantime, however, the tortoise runs 8 meters, because Achilles can run twice as fast. So the tortoise is half as fast as Achilles. So he's run 8 meters, and so he's ahead of Achilles still. So this is just as if Achilles had said, "Okay, I'll give you an 8-meter head start at the beginning." But by the time Achilles has run 8 meters, the tortoise has gone 4. He still hasn't caught the tortoise. So Achilles runs another 4 meters. Well, the tortoise has gone 2. Achilles runs 2. The tortoise has gone 1. You can continue this indefinitely, and you can see that Achilles will never catch the tortoise. So this, of course, is totally counterintuitive, which is why it's called a paradox, and it kind of results from this idea that you can infinitely subdivide space. And it's, you might say it's a result of thinking of space exclusively as consisting of these rational points. Yes, Pat?
Someone just, either I read it or told me one time that one line represents infinity. because the more you could just keep splitting it up forever.
Yeah, exactly. So you can keep splitting up this number line into rational numbers without end, so infinitely. And the number of rationals is infinite. And between any 2 points, you can infinitely subdivide it. And so there are infinite number of rationals between any 2 points. And even after you've subdivided, you can still infinitely subdivide. So it's an interesting idea to contemplate. But it gets even more bizarre, as we'll see in a moment. So even though you can infinitely subdivide space into rational numbers, and even though no matter how far you've subdivided, you can infinitely subdivide even more and still get more rational numbers in there, there are still points that are missing. What points are those? Well, here's 3 of them. The square root of 2, the number e, and the number pi. E is associated with the base of the natural logarithm, and pi, of course, is the ratio of the diameter of a circle to its circumference. But let's look at the square root of 2. It's the easiest one to understand. If you use the Pythagorean theorem and simply look at a triangle whose 2 legs are 1 unit in length, its hypotenuse is the square root of 2 in length. And so this leads us to think that, well, there must be a point on the line that corresponds to the square root of 2. If you go from 0 over to the right, you must be able to lay this triangle up there, and there's a point there. And it's called the square root of 2. But is it a rational number? Well, you can actually prove that it's impossible for the square root of 2 to be a rational number. I won't go through the gory details of the proof, but if you want the details, they're easy to find on the internet, or I'll be happy to talk to you after the talk. But the basic idea is that if you were to suppose that the square root of 2 was a rational number, you find that that leads to a logical contradiction, so it's impossible.
So what's a rational number?
A rational number is the ratio of 2 integers, with the denominator not being 0. So what you would do, mathematically, what you would do is you would say, you would start by supposing that the square root of 2 equals m over n, where m and n are integers. And then you'd start to derive conclusions from that, and you'd find that there's no way you can find 2 integers, m and n, that satisfy that. Mark?
I'm not going to ask another question for this talk, but why define rational in that way? Like, why is it only a ratio that's a rational number? Like, what does that even mean? Why that distinction?
Well, the nice thing about a rational number is you can easily relate them to whole numbers.
Right.
And we know what whole numbers are, and so we want more numbers, as we saw further. We need to distinguish space more finely. So we start with the numbers we have, and we say, well, what are some numbers that are related directly to those? Well, it's the ratio of those numbers, fractions of things. And so that naturally leads to the idea of rational numbers. And but what we've just seen is that that isn't exhaustive of all the points on a line. So how many of these numbers like the square root of 2 pi are there? Are we just missing 3? Do the rational numbers cover every other point, and these are just 3 exceptional points that we just have to say, well, there's 3 exceptions. But otherwise, the rationals have it covered. They're filling up the whole lot. Well, it turns out that there are a whole lot more. And I'll give you a glimpse of the reason for that. So first of all, we have to consider how many rationals are there. Well, there are infinitely number of them, but we have to get a sense of how large that infinity is. And this is where mathematicians really made a leap forward with Georg Cantor and his mathematics of transfinite numbers. Is he defined a way to talk about how relative sizes of infinite quantities. So at first this sounds crazy because infinity is infinity, you can't count it. But he found a way to talk about this, and this is how it works. Normally, when we compare the sizes of two numbers, we have, say, pebbles, and we have digits, 1, 2, 3, 4, 5, and we compare the pebbles to the digits, 1 to 1, and we match them up, and the last number we come to is the number of pebbles. And so we've counted them. That's kind of how counting works. Now, the normal idea of how big something is the last number you reach to, and that's the size of the set. But with infinite numbers, there's no last number, and so all you can really say, you can't really say how big it is, but you can say whether it's the same size. So if we have two infinities and we can match them up 1 to 1, then we say they're the same size. If we can't match them up 1 to 1, we say they're different size. So we'll start with by showing that, and this sounds kind of odd, but this is one of the properties of infinity, is that the infinity of the integers, the whole numbers, 1, 2, 3, 4, 5, and so on, is the same size, in the sense, of all the rational numbers. Now that's counterintuitive because the rational numbers include a lot more numbers. And this is one of the counterintuitive properties of infinite sets, is that it can be the same size as one of its subsets. But here's the way mathematicians show that the rational numbers are the same size as the natural numbers. They write down all the natural, well, they don't actually write them all down. That would be impossible, but the idea is that a rational number is the ratio of two integers. So on the rows, you write integers starting at 1 going off to the right. And in the columns, you write integers starting at 1 going off downward. And every rational number is the ratio of two integers. And so somewhere on this table, if you give me a rational number, I can guarantee it's going to be on this table, because it's going to have an integer on the top, an integer on the bottom, and I just say, well, you just go over that far on the top and that far down, and there's your rational number. So it's in this table. So this table encompasses all rational numbers. Now all we have to do is associate this 1 to 1 with the natural numbers. So the way you do it is you start in the upper left and you say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and you can just keep going like this, zigzagging diagonally back and forth. And there's no end, of course, because the natural numbers are infinite. But you're also going to eventually hit every rational number. You're not going to miss anything. You're eventually going, if you give me a rational number, I go over, I go down, and you say, well, what natural number does that correspond to? And I say, well, I just zigzag here, do. You could actually work out a formula for it. And I could say that's the natural number that matches with it. So every rational will match with one and only one natural number, and vice versa. Actually, there's a little duplication here because 1 over 1 equals 2 over 2 equals 3 over 3 equals. And so there will be actually some natural numbers that...
an infinite number.
Yeah, there will actually be an infinite number of them. So this shows that the infinity of the rationals equals the infinity of the natural numbers. And this is called a countable infinity. That's the mathematician's term for it, because you can count them. You can match them up with the counting numbers. And you can put them in a list. You could enumerate them. You could say how to generate them all, given a process. so those have the same size. Now here are some paradoxes. I mentioned this already, that a subset of an infinite set can equal the whole infinite set. And here's an example that's easier to see perhaps. The even numbers have the same size as all of the numbers, the natural numbers. So for example, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, etc. That's obviously infinite. So is the set 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's obviously infinite. And there's an easy way to see that these are matched up 1 to 1. You match 1 with 2, 2 with 4, 3 with 6. You match each number with its double. And so each member of the even numbers will match exactly one natural number, and vice versa. So you can match them up 1 to 1. So by the definition, those are the same size. Infinities. You can take this also, the odd numbers also match up 1 to 1. You can do the same type of matching except just shift it by 1 digit. And so you have all the odd numbers matched with all the numbers. And so that gives you the interesting result that you can combine two infinite sets, the evens and the odds, and what do you get? You get an infinite set of the same size. So you have an infinity, you have another infinity of the same size. You put the two infinities together, and what do you get? You get an infinity of the same size. And in fact, you can do this an infinite number of times. You can take an infinity of this size, add it to an infinity, and another, and you can do this an infinite number of times, countably infinite number of times, and you still get an infinity of the same size. So here's something that you can add to it, you can subtract it, you can add an infinite amount of stuff to it, and it just remains what it is. It's kind of an interesting symbol, really. So are all infinities this size? This kind of suggests maybe that's all there is. There's just this one infinity, and you keep adding infinities to it. You can even add infinitely many infinities to it, and it's still the same size. Could there be anything bigger than that? Well, there is. That infinity, remember, is the infinity of the rationals. And there were irrational numbers, remember? So the total number of points on a line has to be a number bigger than that infinity we were just talking about. And here's how you can maybe convince yourself of that. Again, it's a proof by contradiction, where we suppose that you can do it, and then it turns out you can't. And so your supposition must have been mistaken. So if we could match up every number on the number line, not just the rationals, but all of them, you could match them all up with natural numbers, then you could write a list of them. And on that list, you would have a natural number and what's called a real number. It's the real number line that includes everything. And a natural number, and that real number, and a natural number, and that real number. And this would go on, just like the list of rationals did. And for every point on the line, you'd have a real number, and that would match one of the integers. Now, the way we show that this cannot be is that we say, I can show you a number that isn't on your list. And the way you do this is by actually constructing that number. So if you give me a list of all the natural numbers and all their corresponding real numbers, I can write down a number that's not on your list. And this is the way I do it. I start with the first digit. I say, pick a digit that's different from the digit in the first number. First digit here is 2, so let's just pick any one of the other digits. Let's say 7. Okay. So this number, whatever it's going to be, it's not the same as this number because it differs in that digit. So we go to the next number here, and we say, well, what's the second digit? It's 9. let's pick a digit different than that. We have a choice of 9 other different numbers, so let's just pick 4. And so this number we're writing down here is different from both the first and the second numbers on the list. So we go to the third number on the list. What's the third digit there? It's 3. So let's pick a digit here that's different from 3. And that's 6. And we go to the fourth digit. It's 2. We'll pick a digit different from 2. It's 8. And so on. So we're constructing a number, and it cannot be equal to any number on this list. And the reason is that no matter what number on this list you pick, there will be one digit at least where it's going to differ. As long as that one digit differs, the two numbers cannot be equal. So this number is not on that list. So the list cannot be complete. Yeah. So this proves that there are points on this line that are beyond this first kind of infinity we're talking about, the countable infinity. That the infinity of all the points on the real number line is an infinity greater than the countable infinity that we were talking about earlier. So there's some kind of infinity even more infinite than that first infinity. This is why mathematicians enjoy mathematics. They get excited by these kinds of ideas. It blows their mind. It's better than drugs. They just think about this stuff, and it's like, wow. Contemplate this, and it blows their mind. So there are different kinds of infinities. As I said, the integers and rationals are a countable infinity. That's the first type. And the irrationals are a larger, what are called uncountable infinities. You can't count them. You cannot list them. You cannot describe them all. You couldn't give me a formula and say, well, here's how you generate all of the real numbers. Here's how to exhaustively spit them out of a computer or something. So they elude descriptions. The way that mathematicians get around this problem is they just say, okay, so we can't explicitly write them all down. Let's just say they exist. Exactly. A miracle has occurred. There exists these numbers. And that may seem like cheating, but the real trick is that nonetheless, they can go on and develop mathematics that's rigorous based on that assumption. And there is a rigorous mathematics of the real numbers, of the continuum. Nevertheless, it's based on this assumption. Kind of hidden behind that is this assumption that this exists somehow, in some sense, even though we can't objectify it. Let's just say it's there. So this continuum of the real numbers is a kind of space. This is really the space that is used in physics to describe physical space. And yet it's all, if you really get down to the nitty-gritty mathematical description of it, it's based on this axiom, this assumption. You just say, well, it's there. We can't name it, really. We can't exhaustively describe it, but we just say that this continuum exists.
Well, are there things that point to the fact that it could exist? I mean, is it a could, or you just take it out of the air?
Well, the square root of 2 suggests that they are there, but that's just one example of a real number. So that says, well, we should have these numbers. They should be there. The square root of 2, pi, and so on.
You said that there were a lot of those numbers, but you didn't actually say more than that. You gave 3.
Yeah. So how many?
Well,
it's what we can say. What we can say is that it's an infinity greater than countable infinity. Now, how much greater?
is that because it's the nature of square roots They're,
It's more than just square roots, actually. If you were to, you could actually list out all the square roots. You take all of the natural numbers and you take square roots of them all. You have a list of all the square roots. And so this is far more vast than just the square roots. There are numbers, all these square roots and stuff, and you can add square roots together and divide them and all of this. All of those numbers are countable. So that doesn't get you anywhere. The numbers that actually make this infinity greater are called transcendental numbers. It's actually what mathematicians call them. They're transcendental. It's an interesting name. So Franklin Merrill Wolff, the American philosopher, mystic, and mathematician, he was trained in mathematics at Stanford. He drew some interesting parallels between mathematics and mystical philosophy. And this is something he said about the continuum, this space of real numbers. It's true that man has arrived at the notion of continuity, although he never really thinks it. And by that, he means exactly what I was talking about a moment ago, which is that you can't explicitly write down all of these numbers. You can just say that it exists, but you can't enumerate them all. So you can't hold a thought of all of those numbers. It somehow transcends thought. Continuity belongs to the hinterland of consciousness. This simply illustrates the eternal fact, that is, that the actual consciousness of man continually operates in a nirvanic as well as a samsaric sense. So in a sense, in the background of all the explicit thinking, we think about these rational numbers, we think about the square roots, we think about all of these numbers, but sort of implicit in the background of all this is this continuum, this continuity of space that we can't actually objectify completely. So, we've failed at coming to some kind of definitive description mathematically of this physical space that science uses to describe the world. But what about measurements? Certainly that's more tangible. We can hopefully grab onto space that way. Well, let's investigate this. Can we grasp the nature of the space that we measure? Can we somehow define it? Well, let's take a look. Let's say you have an object and you want to measure it. One of the properties of space is how tall things are and how large. So what do? We take another object, we call it a ruler, we put it up next to it, and we read off a number. Let's say it's 7.12. Well, that really doesn't mean anything until we say what our units are, right? So after we've measured this, if you tell me how tall is your house and I say 7.12, you'll just kind of stare at me and you'll say, 7.2 what? What are you measuring in? What are the units? Well, they could be meters or they could be yards. If I used meters and you used a yardstick, you'd actually get a different number. You'd get 7.79 instead of 7.12. And if we didn't say what units we were talking about, we'd get these different numbers and we could argue, how tall is the house at 7.12? No, I measured it at 7.79. And we could argue till the end of time and never come to agreement because we're using different units of measurement. So the numbers we get as a result of scientific measurement depend on our choice of the units we use to measure. So this isn't something completely objective. These numbers don't, the house doesn't come labeled with 7.12 on it or 7.79. That number arises in relationship to our choice of a unit of measurement. So we select a choice, and the way science works is that scientists agree, okay, if we're going to compare our measurements, then we're going to use the same units so that it makes sense. Otherwise, science wouldn't make sense. So scientists select what are called standards of measurement, and they all calibrate their instruments back to the same standard so that the results can be meaningfully compared to each other. In addition to choosing your unit of measurement, we also implicitly or explicitly have to choose a method of measuring. Implicitly, we all usually assume that if you're going to measure distance, you just go along a straight path. But it's conceivable that one person could measure distance by zigzagging along the tiles in a floor instead of going straight from one corner to the next. That could be their way of measuring distance. They say, well, I don't measure it this other way. I measure it by that way. And as long as everyone agreed to measure things this way, you could do science. It would work just fine. Because everyone would choose to do it the same way. So the important thing is that you decide on a measurement procedure and then stick to it and have everyone use the same procedure. So the numbers that arise as a result of measurement also arise in relationship to our choice of the procedure we use to measure. So they depend on the unit and the procedure. In addition, these measurements, we write down numbers, numerical representations of the measurement result. But the same numerical expression can represent different numbers. Here's what I mean. The expression 10100, normally you'd look at that and say, well, that's 10,100. But that's assuming you're using base 10. If you're programming a computer and you want to talk to the computer, you'd use base 2, and this is actually the representation of the number 20. So the same numerical expression can correspond to different numbers. So when we make a measurement and we write down what the quantity is, we're implicitly assuming or explicitly specifying the base of the numerical expression that we're using, in addition to the units and the measurement procedure. So all of these measurements we make of space depend on these choices we're making. And if we make different choices, we get different results.
Does the base always have to be an even number?
Ooh, you can work in non-integral bases. For example, the number, you can even work in a transcendental base. The natural logarithms, for example, are base E. So you can do lots of crazy stuff. But it's most convenient to work in base 10 or base 2 or something. So all these lengths and distances in space arise independent on the choices we make. Nature doesn't dictate these choices. We're free to choose however we like. This doesn't mean that everything's just all arbitrary, because we agree on a particular way to do it. And so the results we get aren't arbitrary once we've agreed. So scientists, as I was saying earlier, agree on their units and procedures and ways of representing numbers. And once they've done that, everything hangs together nicely and they can compare measurements and science proceeds forward. But this space, you'll see we haven't managed to grasp onto it in any kind of objective way. As we've seen all these measurements, they're arising in dependence upon our choices we make. Where is the space that somehow has some objective existence? We can't grasp it really, because we see, as we look closely at how these measurements arise, is that they arise in dependence on our choices. So the space doesn't exist objectively out there. And it's elusive. We haven't been able to grasp onto it. So that kind of wraps up the science part of this. Hopefully I've convinced you, or maybe just raised some serious doubts in your mind that scientists and mathematicians have somehow grasped the essential nature of space. They can certainly work with it and describe it and develop consistent theories, but underneath it all, at the root, this idea of continuity is, as Dr. Wolf said, it's in the hinterland of consciousness. It can't be objectified. So let's turn now and look at our immediate experience. Now that we've kind of perhaps disposed of or quieted the intellectual mind's objections that might be raised about, well, physicists really know what space is, or mathematicians really know what space is, or isn't space, something you measure, all of these objections the mind comes up with. Hopefully everything I've said kind of quiets that down, all those objections, and lets them kind of rest to the side, like, well, maybe all of that isn't true the way I thought it was just true. So now maybe there's a space in which we can more freely perhaps investigate our own immediate experience. What is space in our immediate experience? Well, we have these objects that just arise. If you've been outside in the evening lately, you've seen what's close to a full moon out there, pretty glorious. You see that in space. We have tables and chairs typically around us. You might have a teacup sitting on there. Now, I've intentionally drawn or put these objects in here in particular size to illustrate that this image of the teacup is larger than the table and the chair. Right? If I were to take a ruler and actually measure this on the screen and compare it to that, I'd get a bigger number here. But is a teacup bigger than a table? Well, not usually, exactly. So why do we say that? Why do we say that? Because it can appear larger. And a teacup could also appear larger than the moon, but we don't say it's larger than the moon. We know the moon is really, really big compared to a teacup or a table. So if we think about this a little bit, you don't have to go into science here. If you just think about how your sense of space and distance arises, it arises because there are relationships between these objects and how we move between them. So if an object is really close to us and it appears large, it's not necessarily larger than another object that is far away. And how do we know that something's far away? Well, if I start walking towards it, it takes me a long time. This is how time and space are kind of linked in direct experience. Without even getting into Einstein's relativity, we see here that space and time are really linked at a fundamental level in our experience if we really look at it. With the teacup, I don't even have to take a step. I just reach out and I grab it. It's right there. And so we learn, and this becomes implicit knowledge that we don't even have to consciously think about after we're this tall, It just becomes built into our cognitive processing that if things change their size in relationship to movement towards them and away from them in certain ways, then we learn to understand their size in relationship to each other. And this is why in science, or even in direct experience, if we want to get a sense of the relative size of two things, we put them up next to each other. If they're different distances away from each other, we know that we don't necessarily know how big they are in relationship to each other. So this sense of space and size and everything arises in dependence on the relationships between these different objects in our movement, the movement of our body in space with respect to them, and so on. So if we look at our own experience of space, we see that it arises in dependence on these relationships between objects. But how does an object arise? How does that really work? if the space arises in dependence on these objects, if we really want to understand space, we have to look deeper into how did the teacup appear in the first place, or the moon for that matter. So let's look closer at the teacup. To experience this cup as an object normally involves the focusing of attention there in a particular region of the visual field. And that involves implicitly making a distinction in imagination around that cup. So you're distinguishing this part of the visual field from everything else. Does that make sense?
Mm-hmm.
And attention is focusing in, kind of drawing in upon what's inside of that distinction that imagination has drawn around this image. So inside of this cup is what we call the space of the cup, and then outside of the cup is the space of everything else. So to experience this object requires the imagining of this distinction and the focusing of attention within that distinction. And if you can meditate on this, it's an interesting meditation to look at objects and how they actually arise and see if you can notice these distinctions and how they arise. And one thing that's interesting to look at here is that when attention focuses in on this cup, it's ignoring the visual field around the cup, at least to some extent. When you focus in on the cup, you're just sort of, everything else is sort of in the periphery, right, or ignored. But does it disappear? So that's how the cup kind of stands out, is by ignoring everything else. But the cup inside this distinction and the space outside of the distinction are both in this kind of space of awareness. And this space of awareness isn't a physical space, this is just the space of consciousness, if you like. So if you just kind of relax into that space that is prior to the distinction that attention draws, you can maybe recognize that even when attention is focused on the cup and you're ignoring everything outside, ignoring everything outside of the cup doesn't mean that awareness blanks out. Everything else disappears from the visual field. It's just that it's ignored. So, for example, if I'm over here, you can look at me, and then you can move your attention to the cup. Even though you're ignoring me, I'm not in the focus of your attention, you can recognize that the image over here of me is still in awareness. It's not that that awareness has disappeared, it's just that attention has focused on the cup in awareness. So this kind of space of awareness remains, even though attention is doing this activity of focusing in on this, drawing a distinction there. And this is kind of how these objects arise and vanish within this field of awareness. And then you can look further into your experience and investigate whether awareness on these different sides of the distinction, does it arise or pass, or does it just stay there? And then you can ask the question, well, can you really separate the image of the cup from that awareness? Can you disentangle the cup from awareness? Could there be awareness? Could there be a cup without awareness, an appearance of a cup without awareness? Could you separate that cup somehow from the awareness of the cup? So by doing these kinds of investigations, you you can maybe start to get a sense of this space, and this is, again, isn't a physical or mathematical space, this is a space of awareness, that is sort of the substratum out of which arises objects and relationships between objects, which we then call physical space. But below all of that is this much more fundamental space from which the objects themselves appear to arise. And you can also ask yourself, what are the kind of qualities of this space? And there are no definitive answers to this, but some of the qualities that you might read about in some of the mystical literature are things like it has the quality of being aware, being lucid, being open. It can accept anything. It's completely open or empty. It's transparent in the sense that there is no inherent obscuration in this space of awareness. And it's seamless, or it has this property of kind of continuity. There's no distinctions inherent in it that you could find. There is neither seer, nor seeing, nor seen. There's but one reality, changeless, formless, and absolute. And that's basically all I wanted to end with.